In this video, we'll talk about the roots of unity as an application of roots of complex numbers. An important result in complex numbers theory, or in things you might see in classes later on, is the idea of roots of unity. So the nth roots of unity are the n complex solutions to the equation z to the n equals 1, or really they are the n complex numbers. When I raise them to the nth power, they give 1. And now clearly 1 is an answer to this, right? If I raise 1 to any power, I get 1. So z equals 1 works here. But like we saw when we're talking about roots of complex numbers, there's more answers than just that. There are actually always n complex numbers, who when I raise them to the nth power, I get 1. How do we go about solving this out? Well, when you look at the complex number that is 1, and as a complex number, 1 is 1 times e to the I times 0. So my angle here is 0 because I'm on the positive x-axis, and my radius here is 1. How do I find the nth roots here? Well, the nth roots are then zk is the nth root of 1, which is still just 1, times e to the I 0 plus 2k pi over n, or there's the complex numbers e to the I 2k pi over n. Those are all the complex numbers, and there's n of those, for k from 0, 1, 2, up to n minus 1, that all when I raise them to the nth power will give me 1, because they'll give me something of the form e to the I times 2 pi k, and that's just 1. What does this look like graphically? So we're looking at complex numbers of the form e to the I 2 pi k over n. The first thing to realize is these numbers all have modulus 1, which means they're all in the unit circle. What else do we know? Well, the angles are at 2 pi k over n, which means they're evenly spaced with an angle of 2 pi over n between them. And furthermore, we always start at theta equals 0. Which means, say we're looking at fifth roots of unity here. So fifth roots of unity, I'm going to start here. This will be one of mine here. This is 1, or z0. Then I go up an angle of 2 pi over 5, which puts me right about here. I get 1 there. I go 2 pi over 5 further, and then 2 pi over 5 again, 2 pi over 5 again, and then back to 1. So each of these angles here is even at 2 pi over 5. It sets back to 1. So we get actually what would be a regular pentagon out of drawing this shape. They're evenly spaced, everything's equally sized. We get a regular shape out of that with the picture here. You can do this for any n. For any n, if you plot out the n roots of unity inside the unit circle, you will get a regular n-gon out of that shape, which is pretty cool, talking about the geometry of these sort of shapes in the complex plane. As an example, let's find the polar and rectangular coordinates of the sixth roots of unity. So we know what they all are. They're all going to be of the form e to the I 2k pi over 6, or k pi over 3. That means my z0 is just e to the I times 0. My z1 is e to the I times pi over 3. And I can get the rest of my list this way as well. And then we can use sine and cosine values to convert these into rectangular coordinates. This one is 1. Cosine of pi over 3 is a half. And sine of pi over 3 is root 3 over 2. And this pattern keeps going. There's numbers that I get. And if we were to draw this out, this picture here also makes sense, because I should get, on my unit circle, 1, 2, 3, 4, 5, and 6, a regular hexagon from that shape. That's how you can go about finding the nth roots of unity, which are a particular case of finding the roots of a complex number, namely that of the complex number 1.